All right, good morning. Thanks for coming to session B for evacuation modeling. If you're hoping for fire modeling, it's down the hall. But this should be a great set of speakers this morning. We're going to get started. Are you okay. All right, we're going to get started with Richard Peacock from NIST, talking about the predictive capability of fire and egress models, and really focusing a bit more on the verification validation side of things. So I'll turn it over to Rick. Thank you.
Thanks. Thanks, Brian. I kind of look at myself as the transition from fire to egress here because I'm sort of walking a line between both of them. At NIST, we've been looking at fire model validation since at least the mid-1990s, with thankfully some success recently. And I think there's a lot of ways that work can translate over into egress modeling as well, but I also think there's stuff that the fire modeling side can learn from egress modeling. So that's kind of the tone of my talk today, I think. Yesterday we heard quite a few different views of validation and verification. Craig and Steve started off yesterday from a user's point of view, looking at what the user's responsibilities and roles are in validation. And it's basically to make sure that what the tool you are using is applicable to the problem you're trying to solve. On the other hand, we modelers look at it from a bit different point of view, and our role is both verification that we're doing it correctly, as well as broad a range as we can of validation. If you notice, the title of the slide avoided the word validation. And the reason I do that is simply because I don't think we ever really reach a truly validated model. We have tested it for some part of the space that it's applicable for. And if we had tested it and understood its entire space, we wouldn't need the model. We'd be able to go back to standard engineering judgment. So I think, and there are certainly other views of validation and verification. And so I'm taking a little bit broader overview of the whole topic of verification and validation today. But it is very much from a model developer's perspective. There are a number of different standards. You heard a little bit about them referenced yesterday. Most noticeably, we talked a bit about ASTM E1355 that provides an overview of a process for model validation with details in some areas and very little information in others. There are a number of companion documents, a couple of which may go away in lieu of the SFPE guides. But those do still exist, and they do other components of it, of trying to better define what documentation should accompany models and identifying limitations in models. There are ISO documents that are roughly equivalent. They sort of evolved at the same time, but they're taking a bit of a diverging path, but there's still very similar information in the two. Probably, and overlying all of those are government regulations that make use of these. Most notably here, NFPA 805 has been a strong driver of better understanding of fire model validation by requiring validated models for use in nuclear power plants. On the egress side, the International Maritime Organization has requirements for egress models that for passenger ships that basically test the capabilities of the models to some extent. In model validation, it's all about the data. How much data do we have and what quality of the data? But the documentation is basically the starting point. There's usually technical documentation that goes with a model that provides in-depth, intended at least, in-depth explanation of what the models do and how they do it. The fact that Kevin and I routinely answer almost daily questions on the internals of CFAST and FDS says there's more we could add to that documentation, because clearly not everything is in there. Users manuals hopefully provide details on inputs and outputs of the models. And then there's accompanying guide, one or more accompanying guides for validation and verification of the model. Typically, the verification is mathematical verification, but there are other tests that we'll get into in a bit. And validation is comparison with experimental data. And it's that data that forms a large part of the second half of my talk. For CFS and FDS, we basically started with the work we did for NRC, which you heard about new Reg 1824 yesterday. Both the CFS guide and the FDS guide have built on that, adding additional information, but keeping the same overlying structure that was in new Reg 1824. Let's go back a little bit though, before we talk more about validation, and to kind of get a state of the literature of validation. All of these, with the exception of the last two, are direct quotes from peer-reviewed literature talking about model validation. And I take two things from that. One, the models are great because all of the comments are positive. And secondly, it's almost all qualitative. We're finally beginning to get away from that, but in the literature, that's kind of the state, that's the quote-unquote state of the art. The models always look good, they always provide reasonable predictions, with a few exceptions. We saw yesterday, and we at NIST are to some extent also guilty of this. We had a hand in inventing colors to indicate the level of predictability of models. We are trying to move away from that somewhat. We heard a quote, and if Jim Quinteri's in the room, I apologize for taking slightly out of context. Quote from yesterday, are the models providing good, fair, or excellent agreement? Again, qualitative. They do serve a purpose, and we'll talk about that a little bit. But for engineering applications, as you saw in Kevin's talk in a lot of detail yesterday, we want to move towards understanding things quantitatively. From the qualitative side, and it's not totally qualitative, IMO has a series of tests for egress models that provide what seem to largely be common sense tests for the models. Does it do what you expect it to do? If you put a person in a 100-meter hallway that's moving a meter a second, does he get to the other end in 100 seconds? There are a number of them for walking speeds in corridors and on stairways. This particular example is something, thank you, Timo, I liberated from one of your manuals on walking speeds down a stairwell as one of the tests for FDS plus EVAC, one of the IMO tests there. There's also tests on exit route allocation for large buildings and or large assembly halls that have multiple exits. While all of them don't provide specific quantitative criteria for acceptance, they still provide a level of verification and validation that the model is doing what you expect it to do. From a quantitative side, there's kind of two pieces to model V&V. There's the verification, which in our mind is really sensitivity analysis plus verification of the model. That looks at, is the model doing what the developer thinks it's supposed to be doing and what he documented that it said it should be done. For CFS and FDS, it ranges from either chapters on CFS side or an entire manual on verification for FDS. But in both cases, what it lacks is a structure that's guided by consensus standards. So there's a tremendous amount of information from the obvious ones like, does the model actually do an appropriate mass and energy balance, which this is taken straight from the FDS manual, to sensitivity tests, which this is one out of the CFS manual, of how do the outputs change based on a range of inputs. all of those don't really tell you whether or not the model's providing an accurate answer. It's, is it being consistent within itself? But in both CFAST and FDS and other codes manuals that we've looked at, particularly in the sensitivity and certainly in the consensus standards, there isn't a lot of guidance on what kinds of things should be in there on the fire side. The standards are ripe for a corollary to the IMO tests for fire modeling. From the obvious ones, like, is it doing an appropriate energy balance? Is it doing an appropriate mass balance? Can you prove that? To more esoteric ones, particularly for FDS, that test individual submodels. In FDS, we heard a bit about that yesterday from Randy. From CFAS side, there's a number of correlations built into it, from plume flow correlation, vent flow correlations that are making use of correlations based on experimental data, but there needs to be verification of that. So in all cases of the models, the fire models are even riper for improvement in the standards and requirements for verification than are the egress models. Transitioning from sensitivity analysis to more quantitative comparisons, it's all about the experimental data and how much you have, what a broad range it is, and the quality of the experimental data. Some of the quality data, and I will say, although I'm probably getting a little bit ahead of myself, there's been a lot of discussion about the need for blind testing of models. And from at least the developer's point of view, blind experiments are good exactly once, then they're no longer blind. The industry and field doesn't have money to continue to test things just so we can have blind tests. So we rely on existing test data. This particular test, which is built into the new Reg 1824, the CFAS validation, the FDS validation, is a series of tests that's about 25 years old at this point that we did at NIST with 3 rooms. This is a shot down the corridor where we're looking at temperatures in the corridor, gas concentrations in the corridor, but the measurements are there. The measurements are there and the definition of the test is there, sufficient for us to do modeling. The key is doing it right. The key is understanding what we have in terms of the experimental data, some of which is very old, and understanding the model inputs. And there's almost 2 sides to providing good quality simulations. One is what has been termed an open experiment, open comparisons, but in our mind it's also almost how good can the model possibly be for a given application. If you know everything about the experiment you're trying to compare to, how good can your model comparison be? That provides an assessment of the quality of the model itself. That's somewhat separate from how good can the user do that. That's the purview of round robins. That's something that still is evolving over the last 20 years without a whole lot of success. What's the range of values you get for the same simulation from a range of modelers? Quite often it's a wide range of answers. That's training, that's better documentation from our modeler's point of view, developer's point of view. But what we're going to focus on and what we at NIST have focused on is the first half of that, which is how good can the models be if we know what we can about the experiments. Kevin and I spent the better part of 3 months understanding complementary inputs in CFAS and FDS, so when we're running the same test case, we know we're at least using consistent inputs. That was not a trivial process. We've been going through the same thing with some egress tests. We've developed an implementation of an elevator model from Claude and Bukowski and stairs egress from the SFPE handbook, putting that together in a simple Windows tool and looking at validation of that. This is some of the data that we collected at NIST from one of 12 buildings now, 13 buildings now, have egress time, time from alarm versus an occupant number, and essentially giving you an output rate from the building for this. Understanding the building, even with tests that we ran recently, takes some doing, because there are parameters in the inputs that may or may not be in the input data, and sometimes we have to go back and find those data again. That was particularly an issue with this particular data set. We are growing our validation sets all the time. FDS has grown from about 6 test series that we heard to 42 or so. CFAST has grown from that 6 to about 12. We've been able to build very much on what FDS has done over the years in open source and cooperation. We're carrying all of that over to CFAST. But the message to take away from it is data is not data. You've got to have good quality data, and it's a tremendous effort to make sure you're using it correctly and understand what's really there. I think I've actually talked about that. You've seen a couple of these. This is just another indication that we need all kinds of data. We have some fraction of the data we need, but it is only a selected fraction of the entire space of the model. Same thing is true for evacuation models. We have some data. NIST has been collecting quite a bit of data over the last few years, looking at movement speeds in stairs. We need complementary information to better understand movement towards elevators, and some of the submodels you hear about what impacts people's movement speeds in terms of behavior in the next talk, I think. I think I've actually already talked about this earlier in the talk, so I'm not going to worry about it. Again, this is another look at all the data that we have collected compared to the correlation of SFPE. What we take from that is, again, another look at the data is this is real data, so it's not going to lie perfectly on a curve. The SFPE calculations and correlations are just that, but we have to understand there's uncertainty in simple calculations just like there are in the more complex models, that there's quite a range around what the correlation says, so that needs to be thought about when you're doing a simulation and depending on the results. We heard yesterday talking about uncertainty, but even getting to that point of what do you use to compare a model to an experiment? Do you use a peak value? At this point, all the stuff we've done has been basically based on peak values. There's a lot of other ways. This is just an example. If you consider the made-up example, consider the dots, the experimental data, and the 3 different curves as some model representation of that. Peak value agrees in all of those. They're dramatically different, though, in terms of the real predictions. Same thing is true of real data. This is a single-room post-flashover test that was done at NIST, 35 years ago, and measuring upper layer temperature in that compartment in 2 different spaces. There's close to a 300 degree different measurement of that. How does that correlate to what you're comparing to the models? Helps you understand the uncertainty in the models and the uncertainty in the experiments. We're just beginning, as Kevin talked about yesterday, we're beginning to have a handle on what to do with the uncertainty in the models and the uncertainty in the experimental data and be able to make quantitative assessments for that. So I guess the message that I take away from the current state where we are in model validation is that the standards are there. There are good pieces and requirements for egress models. There are good pieces and requirements for predictive fire models. They overlap, but there are areas both sides can learn from each other. Documentation by the modelers and validation efforts by the modelers is key to the use of it. Both qualitative and quantitative assessments have their purpose, but neither is a whole without the other. and we still need data. That's always been the case for the last 25 years. I've been thinking about validation, and it's still the case. We have parts where we understand it very well and parts where we just don't have the data. And so that's where we are. Thank you.
Thank you. Thanks, Rick. We have time for just a couple quick questions if anybody has anything. No? Okay. Thanks a lot, Rick.
Thanks.